We are going to conclude by talking a little more about adiabatic processes. This is where the book really dives into adiabatic processes, but I think they're pretty important, so I've introduced the bulk of the material about adiabatic processes already. So if this is the first thing you're seeing on adiabatic processes, you've definitely skipped some earlier videos. But to summarize, the adiabatic process is defined by Q equaling 0. Again, either it's so fast that heat is not exchanged, or, which is the version I like better, we say that the system is so well insulated that heat is not exchanged. And our specific process could fall into either category. So make sure that you're recognizing either description as being an adiabatic process. Now, we know two things from both the first law of thermodynamics and the specific heat of gases. We know how the thermal energy, or change in thermal energy, relates to a change in temperature. And again, the molar specific heat to use here is the constant volume, 1. And from the first law of thermodynamics, we know that the change in thermal energy is going to equal the work plus the heat. But now, for an adiabatic process, we know that the work done is just equal to this value, where again we have the number of moles times the constant volume specific heat, molar specific heat constant, times our change in temperature. So the reason that this is interesting is because these adiabatic processes have really complicated shapes. We haven't previously described how you would draw those shapes. We've described what isothermal lines look like, isotherms. We've described the very simple shapes that isobaric and isochoric processes have, but we haven't defined the shape of the adiabat. And the adiabat is the special curve that an adiabatic process actually follows. But now we can define the shape using the fact that the work relates in this coefficient, so this is a constant, multiplied by our change in temperature. Now the math to actually define the shape is a little bit complicated. The book goes through it, but I think it's helpful to mostly understand, again, kind of these bigger pictures, like the first law of thermodynamics. So I encourage you to refer to the book if you want to know where the definition of the shape is coming from. Adiabatic curves are the most complicated shape that we're working with in this, and it's something that will come back a little bit later when we talk about cycles. So that's why it's important to talk about it now at all. So remember that the adiabatic curves are curved, but they're not isotherms because you do have a change in temperature. So the way that these complicated curves are defined is that P times V to a power has a constant value. So what is this power? And the symbol we use for it is gamma, which is called the specific heat ratio. It is Cp divided by Cv. Now again, we've said that for monatomic gases, Cp and Cv are basically all the same. For diatomic gases, again, they're all the same. So gamma is just a fixed value depending on whether you're talking about a monatomic gas or a diatomic gas. That's really the way to think about it. So these adiabats actually have a slightly different shape if you're talking about a monatomic gas or a diatomic gas. So again, we're saying that it's P times V has a constant power. And again, that power is not necessarily 1 or 2, it's this weird decimal power. So how can we think about this a little more simply? Remember that our isotherms were defined by hyperbolas, that basically P equaled A, where A was some constant, over V. And you can use the ideal gas law to figure out exactly what this constant is, but I want to focus on the relationship between P and V. So it was a constant over V, and you got these hyperbolas, these isotherms. For adiabats, you now have a different constant. Again, we're not really worrying exactly what, it depends on what state values you're at. But now that V is to some power which is slightly greater than 1. So this is like a curve that is slightly between a 1 over V curve, or a 1 over X curve, let me simplify, and a 1 over X squared curve. Right? So a 1 over X squared curve has a sharper fall than a 1 over X curve. The isotherms are 1 over X curves. So your adiabats have a slightly sharper fall than your isotherms. So that's one way to think about it. Again, the exact derivation of where this comes from is a little complicated in the math and not the most important thing. My hope would be that you can recognize when you have an adiabatic process and that you could roughly sketch the adiabatic curve correctly. And one of the ways that you can do that is comparing what an adiabat looks like to an isotherm, and in particular recognizing that adiabats must cross an isotherm since an adiabatic process does change temperature. So that's the most important thing here.